My name is Courtney Lemon, and this is the second lab for the Flip section of Modern Physics 1. In this lab, I focused on identifying factors that contribute to the net force of something that falls slower than a rock when dropped from rest. I chose to use a fundamental principle, the momentum principle, to help me understand the changes of my system, as well as conclude the velocity changes over the period of time are due to interactions of gravity and air. The momentum principle relates positions, vector r, measured in meters, velocities, vector v, measured in meters per second, and the total force or net force measured in newtons or the SI units of kilograms meters per second square. For this particular lab, I captured motion of a falling object and got position and time data from the program tracker. I used this information to see if I could identify what factors contribute to F net, the net force. Here you can see I chose to observe the motion of a coffee filter paper being dropped from rest. The turquoise tracks of the paper generated a table of time in seconds and positions measured in meters. With my system being the coffee filter, I chose to align my axis so y coordinates are in the j hat direction, x coordinates are in the I hat direction, negative is down and to the left, and positive is up and to the right. Based on my video, I see two major components contribute to FNet. Earth exerts a force that depends on a gravitational pull towards Earth in the mass of my system. The air exerts a force that is proportional to the system's squared speed and direction of its velocity. Non-zero components of these forces are known because the force from Earth, or weight force, is down towards the surface of Earth. Non-zero components of the force from air, or drag force, has same non-zero components of velocity. The positions are only changing in the j hat direction over time. Therefore, velocity changes are only in j hat direction as well. Once I ID'd my forces, I used v-idle to construct models to predict how FNet would affect the motion of a falling system. First, I set initial conditions. I put in the mass of a coffee filter, set it to be dropped from rest at the origin. I set the clock to start calculating at 0 seconds and set a small change in time of 1/1000th of a second for models that will closely match my video observation. I set conditions necessary for FNet. Next, I defined the forces that contribute to FNet and made two models. One model uses both the weight and drag force, and B is set to a scalar 0.001436. The second model only takes weight force into account, and B is set to equal 0 for drag force. The while loop is where I insert FNet. It is set to iterate over 1.833 seconds. FNet is calculated, velocity is updated, position is updated, and the clock is advanced. When FNet is just weight, represented by yellow arrow, the magnitude of force is 4 times greater than with drag. The blue arrow represents the presence of drag. When I compare model with drag to my data from tracker, I see my end position closely matches the model's end position. This is further displayed on a position versus time graph. Does any model show terminal velocity? The models with drag show terminal velocity. Velocity can be viewed by examining slope of each line. When fitted with linear trend lines, it appears the slopes of models with drag become constant. The models with drag reach a constant velocity, which means net force is a zero vector. But because the system is not at rest, it is said to be in dynamic equilibrium, and weight force is equal to drag force. If I change the duration of motion to iterate over a period of 60 seconds and print the following properties, I see that though FNet is still slightly changing and not yet zero vector, weight and drag are nearly equal and cancel each other out. What if the system was initially thrown instead of dropped from rest? I used v-idle to see what would happen to terminal velocity over a period of 10 seconds of iteration. I saw the final positions only varied slightly when an object was dropped from rest and dropped with some initial velocity. I plotted the two scenarios on the same graph and saw a constant velocity. After fitting the two models with an r-squared equation, we are able to better observe the close match of the models. The terminal velocity will differ from the terminal velocity of an object dropped from rest because the change of velocity over time is different. However, in both cases, FNet will be the zero vector because the contributing forces will offset one another. Thanks for watching.